So the went up. So suppose a basis is given, how to generate a topology. Suppose a basis B for a topology on X be given, then we can generate the topology. Let's say tau, the name of the topology is tau, in the following manner. What is that? The thing is that we will say that X, U is a subset of X, is in tau if and only, okay, if and only for each X belongs to U, there exists an element, let's say Bx, in that collection such that X belongs to Bx subset of U. So that's how we are generating the topology. We are saying that a subset U will be in that collection. So we are forming a new collection taus will be in that collection if and only for each X belongs to U, there will be a member from the collection. It's not visible? It is. That time will. It's a key. Okay.
Share again. That screen.
Is it visible?
Okay. So that's how we generate the topology. Now it's a routine task to check that it is actually a topology. Okay. We are not spending time on basic topology. I assume that almost all of you have some basic idea of topology. So depends on that. I'm just giving overview of it. Okay. So for each X, if you have this, then we have a basis. Not only that, if we have a collection, so other way we can say that also. Let's say C be a collection of subsets of X. Then C is a basis for a topology tau on X if. So now let's say we know that topology tau and we want to know whether C is a basis for the topology or not. What is the criteria? If for each X, if for each U belongs to tau and X belongs to A, we have, if for this, we have an element Bx belongs to C such that X belongs to Bx contained inside of U. So what's going on? So suppose you know a topology is given and you want to check whether a collection of subset of X is a basis for the topology or not. How to check it? If we choose an element U from the tau and X is a member of U, okay. And then obviously there will exist a member Bx from that collection which will contain the member X and will be inside of it. Okay. So then you know that that collection will form a topology. That it's a basis for that topology. Okay. So that means what? It's a two-way. Suppose you know a basis for a topology, by this formula you can generate the topology, and this way, suppose you topology is given, you can check whether a collection is a basis for the topology or not. So you can verify. Okay. So this you can generate it, and here you can verify it. Okay. So another thing is that from a given basis you can generate topology another way, like if you take the all possible union of members of the basis, so that collection will also going to form a topology for the for which that is a basis. Okay. So, but most cases will use this two factors. Okay. This is how to generate topology, and this is how to check whether collection is a basis for the topology or not. Okay, so related to the basis, there is one more concept that's called pi base for a given topological space. So let's say x tau be our topological space. Let C be a collection of open subsets of X, then C is called pi base, or pseudo base is also called pseudo base. But in general, we don't use this word. Nowadays, we say this pi base. If for each q belongs to tau, there exists, let's say, an element P from the collection such that P is inside of Q. You can see that a basis is always a pi base, because a basis means you choose an element from this, you're always going to have a basis element contain that element and will be inside of Q. So pi base is a quicker, it's not a basis but it's a pseudo base. It's saying that what each Q belongs to tau, whatever open set you will choose, you will have another open set from that collection such that P will be inside of Q. Okay, so that's a pi base. So sometimes we'll use pi base instead of base. Okay. Good. Okay. So now we are saying an element of a topology, the collection is an open set. Now let me define a closed set. What do you mean by closed set? So definition is that you already know, but let me put it. Subset A of X is closed if it will be called a closed set if X minus A belongs to tau. So if X minus A is an open set. Okay. So then we'll call it is a closed set. So that means take the complements of the elements of tau, you will get the collection of closed subsets of the X. It might possible a set at a time can be both closed as well as open. Okay, it's not like that. If a set is a closed, it cannot be open, but it can be both closed and open at the same time. The set X itself is both closed and open. So not only the improper subset or empty sets, but even any proper subset also can be closed and open. For example, if you take tau is a collection of all subsets of X, that means the power set of X, that will form a topology, and we call that topology as a discrete topology. There every set is open as well as closed. Okay. So anyway, so this definition we made. So now we are saying we are defining the closure and interior of a set X. So let A subset of X then the interior of A is the largest open set contained in A. Okay. So it's the largest open set contained inside of A. So another way to say that if we collect all the open sets inside of A and take the union of all those open sets, you will get the interior of A. Okay. So another way to say, okay, I'm not putting it. So just remember this: if we have all open sets inside of A and take the union of that open set inside of A, then you will get the interior of A. Okay. And similarly, so interior of A is defined that way. The closure of A is the smallest closed set containing A. Okay, so now closure is the smallest closed set containing A. So interior is inside of A, but the closure is containing it. So whatever closed set you have containing A, if you now take the intersection of all those closed sets, it will be a closed set. Why? Why the intersection of closed sets will be in closed sets? No, not for finite intersection. Whatever you have a collection, arbitrary collection of closed sets. If you take the intersection of all those closed sets, you will get a closed set. Why? Yeah, because the second property of topology, it says that if you take arbitrary union of open sets, then so if you have intersection A alpha, where A alpha are closed, so if you now take the complement of A, it will be union x minus A alpha. So each x minus A alpha is now open. So arbitrary union of open set by axiom 2 is open. So therefore this complement is an open set. Hence this intersection is a closed set. Okay. So because of that, if you take collection of all closed sets containing A, you will get the closure of it. So that's why it's called the smallest closed set containing A. So closure of A is the smallest closed set containing A. Okay, we'll use this notation. So for interior of A, we'll use to denote, or sometimes we'll just quote this notation. It's interior of A. And we use A bar or just write CL of A to denote the closure of A. Okay. So these will use to denote interior of A and closure of A. So these are the notations. Okay, I am not spending time on giving some elementary example. So in the real analysis, you are already familiar with the example of closed set and interiors. So you can use that example over here as well. Okay. So definition: let A be a subset of X, then A is said to be dense in A if A closure is equals to whole of X. If the closure of A is whole of X, then we will call A as a dense subset. Okay, so dense in X. Okay, so I said will be called a dense in X if A closure is a subset of X. Obviously, X itself is dense in X, but we can have other set which is dense in X. Like if you consider the set of a rational number which is dense in the set of a real number, or irrational number dense in Okay, so these are the concept of plane set in X. Okay. The next concept I'll just go through, that's the concept of subspace, subspaces. So, what do you mean by subspaces? Let Y be a subset of X. So, a non-empty subset in general we get. So, let Y be a subset of X. Then, if you take the collection U intersection Y such that U is an element of tau is a collection of subsets of Y, then this collection will form. So if we have a tau and let's say let me denote it by the collection tau Y is a collection of subset of Y, then you can prove that then this tau Y is a topology on Y. Okay. This is just very routine task to check that this will form a topology on Y. Okay. So when we have, so now you can see that we have a topology on X, it is inducing a topology on a subset. Okay. So in this case, Y obviously a topological space, and because Y is a subset of X, that's why we will say that Y is a subspace, topological subspace of X. Okay. So Y in this case, Y will be called a subspace. Okay. By the way, if you know the basis for a topology on X, if you take the intersection with the element with with Y, you will get the basis for the subspace topology as well. Okay. So that's the way you can discuss the topology on Y using the topology on X. So just let me put that remark. So let beta be a basis for a topology tau on X, then this Y, which is B intersection Y, such that B is a member of beta, okay, is a basis for tau Y. So this will be the basis for the subspace topology. You see that I put like a basis for a topology. So that means you can have two different bases for the same topology. Okay, so two different bases can generate the same topology. That's also a possibility. Good. These are the basic things you just need to know before we move into the main topic. Okay, another thing. Okay, so let me just put this the compact set a little bit. So what do we mean by compact set? Definition. So let A is a subset of X, then a collection, let's say C of subsets of X is said to be a cover of A. So said to be a cover of A, so we are defining cover of A. If for each A belongs to A, there exists an element, let's say C from the collection C, such that A belongs to C. Or other way to say that this small c. Okay, so let me like C1. Other way, so you can say that A is a union of you can have the collection of subsets. A will be union of the members of C. A will be subset of the union of members of C. So if the collection C is a collection of open subset of X, we'll say that it's an open covering. So if C be the is the bigger C be the collection of subsets of X that covers A, then C will be called an open covering of A. So if you want to make it more specific, you can say that C is an open. A is covered by open subset of X, because we have the notion of subspaces. So sometimes we we want to distinguish what from where we are taking that open set. Okay. So when nothing is mentioned, like C is the collection of subset of X that covers A, means we are just saying that okay, when we say the collection of subsets, it's also by definition means open subset of X. Okay. But it might possibly we have a collection of subsets of A itself, and that will cover A. Okay, that's also a possibility. Like for example, if A is X itself, so then we have a collection of open subsets of X which covers X itself. So definition. So a topological space X is said to be compact if every, so it's a definition of compact set, if every open covering of X has a subcollection, has a finite subcollection which covers X. So what do you mean by that? Let's say we have a collection of open subset such that X is a union alpha belongs to this U alpha. Okay. So then it is saying that there will exist finite number of elements U1, U2, UK from this collection U alpha belongs to this index set such that X is a union I equals to 1 to K U1. Okay. It will be like that. So X can be written in the finite. So you can think about that. You have a space, whatever you can always whatever open covering you have in the space, you can always find a finite number of elements from that collection which is going to cover the whole space. So that's the idea of compact subsets of X. Okay, it's actually similar to the idea of compact sets in a real line. Okay, just we instead of real line we are considering open sets of an arbitrary topological space. Okay. Next definition. A topological space X is said to be locally compact if, this is a definition of locally compact set, if for each x belongs to x, there exists an open set U and a compact set K such that x belongs to U and U constant inside of K. So that means each point has a neighborhood which contains inside a compact set. Okay. So this is when you have this criteria in a space. When a space has this property, we call that space the locally compact space. A topological space X is said to be locally compact. So each point has a neighborhood in the sense that it is an open subset which can be put inside a compact set. So, okay, well, let me ask you whether a real line is a compact set with usual distance metric. No, is it locally compact? Yes, it's a locally compact. Whatever point you will choose, you can have this one. So in real line, x equals to r with usual topology. Then for each real number r, your u is x minus 1, x plus 1, and your k is closed interval x minus 1. That's it. So, although the real number space, real line is not a compact set, but it is a locally compact space. Okay. So these are the basic things you know before we move into the main topic. Okay. Now we have to make discussion. Definition. A subset, let X be a topological space let an A be a subset of X. Then A is said to be nowhere dense if A closure, if the interior of A closure is empty set. If interior of A closure empty set. So that means A closure cannot contain an open set. There is no open set which will be inside of A closure. So for example, I'll give you an example, but before that, can you see this? If per se A is nowhere dense, okay. So I'm writing a statement. Tell me whether it is a true statement or false statement. A is nowhere dense in X. If and only if X minus A is dense in X. Okay, so before that, I just tell you one property of closure I forgot to mention. So, say, an element X belongs to A closure if and only for each open set U containing X intersects A. So if X belongs to A closure, if and only, so it can be use this criteria. So X belongs to A closure, if and only, whatever open set you have, if it contains X, then it must intersect A. Okay. Now think about that. Let's say we have a subset E, which is dense in X. That means what? Whatever open set you will choose from X, it will going to intersect E. Why? Because let's say that U be an, obviously I need to say a non-empty open set. Be a non-empty open set. Non-empty open set. Then what? Let's say X belongs to U. Now X belongs to U means X belongs to E closure. And because X belongs to E closure, so obviously E will intersect E. So that means if you want to check whether a set is a dense or not, what you have to check whether it intersects with every open set or not. Okay. So whatever open set you will have, if it intersects with that set, then the set is dense in the whole space. Now we are saying A is no more dense in X, even only X minus A is dense in X. Check whether this statement is a correct statement or not. So X minus A dense in A means what? Whatever open set you will consider, it will intersect X minus A. That means that open set cannot be inside of A. Correct. So whatever open set you will consider, let's say U be an open set. It will definitely going to intersect A. So therefore, it cannot be in the interior of A closure. I think I made a mistake. Yeah, I think it should be this one. A is no more dense in X, if and only X minus A closure is dense in X. Now we have, if this intersect, obviously then you cannot be in the interior of A. Because if U is the interior of A closure. So obviously interior of A closure is subset of A closure, so it cannot be in the other part. Okay. So this implies that interior of A is an empty set in that way. Why interior? Again, interior you can use that, choose a point in the interior, then obviously you will have an open set containing that point and will be in interior of A closure because it's an open set. Okay. So this implies that interior of A closure is empty, so therefore A is nowhere dense. And other way, if A is nowhere dense, then X minus A closure is dense in X. Because whatever open set you will choose, it is not in interior of A closure. So that means it must intersect okay, I think I should not read it. Let's say you have interior of A closure is an empty set. So that means what? Whatever open set you will choose, what will happen? It will be not in the interior of it. Okay. So or each open set U intersection A closure, I mean X minus interior of A closure is non-empty. X minus A. Interior is empty. So this is
intersection X will be on. X minus interior of A closure is.
oh yeah, that will be U in itself, and therefore
X minus A closure A interior of A.
no, I just want to ultimately it will be, but what is going on? So U will intersect X minus A close. Okay. Fine. Okay. So next thing is that I am writing another statement. If A is no higher dense, then its closure is also no higher dense. Okay. Next statement is A is nowhere dense if and only A closure is nowhere dense. Why it is so? Why it is so? A is nowhere dense if and only A closure is nowhere dense. So A is nowhere dense means closure of A has empty interior. Now A closure of A closure is A closure itself. Okay. So because of that you have this following facts. So if A was nowhere dense, then its closure also nowhere dense. Similarly, if A closure is nowhere dense, then A is nowhere dense. Okay. Good. Is it clear till now? Or if you have a question, you can. So what we learned till now, if A is nowhere dense, then X minus A closure is dense. And second thing, A is nowhere dense, if and only if its closure is nowhere dense. Okay. Okay, so can you give an example of a nowhere dense set? Okay, by the way, if we consider the real line, let me ask you. Let X equals to R with usual real line display, with usual topology. And let's say A is a set of all rational numbers. Is it a nowhere dense set? Because A closure will be the R itself. So obviously it's not a nowhere dense set. So A is not a what about if I take A equals to Z, set of all integers? So it's a closed set. A closure will be the Z itself, and you know that Z contains no interior point. All the points of Z are non-interior point. I mean, whatever point you choose from that, you're not going to find an open interval containing that point, only contain integers. So this is an example of a nowhere dense set. Let's take R with finite complement topology. So I hope you remember what is finite complement topology. So a member is in tau if its complement is a finite set. Okay. So Rx is R with finite complement topology. Let's say A equals to Q. What is the closure of A in Q? A is a finite complement topology. Okay, let's say whether it's a okay, so obviously you need to know about the closure of Q, otherwise you cannot say anything. Closure will be the full set, is it?
Those sets in
Yeah, closed set are the finite set itself. So, and obviously the whole of R, that's also a possibility. Because that's also there. Okay, finite complement, not only the finite set, and also you have to take the union with Q, phi and R. The whole, because by definition, empty set should be there. Okay, so R, if you have R, then obviously empty set will come. Because the complement of R will be the empty set, so it will come. So if you consider empty set only, then it's fine. So finite complement topology means collection of all subset of R whose complement is a finite set, union empty set. Because empty set in general is not coming, because in complement of empty set is a whole of R, so which is not a finite set. Okay. So in that way, that's correct. So what he said, so if you look over here, what are the closed sets in a finite complement topology? Here are the finite sets are the closed sets as well as empty set and whole of R. Now because Q is a countable set, so this obviously implies that A closure is whole of R and therefore it will contain interior point. So it's also a not a nowhere in set. So if we consider A equals to J, what will happen in this case? Is it a closed set in a finite complement topology? We just learned that finite complement topology, only finite sets are the closed sets. Obviously, you have the whole set R and empty set. So J is not a finite set, so obviously it's not a closed set. So its closure should be the whole set because closure contains J and finite set cannot contain J. So again, it will be whole of R. So whole of R means it will obviously has interior point. Okay. So it's also not a nowhere in set. Okay. Is a finite set a no-Hygiene set? In this case, a finite set is it a no-Hygiene set? It looks like you are not understanding at all. That's indicates that you have most of you forgot about topology. Okay, so anyhow, I have to continue. So let's say A is a finite set. What will be the closure of that set? The set itself. Will it contain any interior point? No, because here you need a whole. I mean, here infinite sets are actually open sets. Finite sets are not. Okay, I am not talking about phi and phi. So if we consider A as a finite set, if A is finite, then it will be nowhere. What about discrete topology? Are you discrete topology? Where Q will be nowhere dense or dense? So every set is open as well as every set is closed. So Q will be a closure of Q, but it also contains Q itself. So obviously, it's every set is not a no-Hygiene set, not a no-Hygiene set over here. So that means it will be a dense set. If a set is not nowhere dense, does it mean that set is a dense set? No, it's also not true. Because Q closure is not the whole of R. So be very careful. So nowhere dense, not nowhere dense does not mean that it is a dense set. Okay. So it's a different thing. But if you know a set is nowhere dense, then obviously its closure complement is dense set. Okay. So be very careful. That's
But in the previous statement, you even previously.
which one?
Previously.
Here, this one.
H nowhere dense.
Dense. H can always H minus A closer is dense.
It is better. Suppose that say we are studying.
No.
Some set is dense in X. That
Now you have not nowhere dense. Not nowhere dense cannot satisfy this statement. So if we have not nowhere dense, then it will satisfy this statement. But if you have not nowhere dense, it will not going to satisfy this statement.
if this statement is that same it implies this same.
Yeah, also implies, but X minus A closer is dense. So let's say we have a discrete topology, correct? Is Q closer? What is Q closer in discrete topology? Discrete topology Q closer will be Q itself. Then what about X minus Q? It's all rational. Irrational. So anyway, whatever is rational, irrational. Is it dense in space? No. So obviously, so that means does not mean that Q should be.
But if we take the real time user topology,
Usual topology is fine, but
that is dense. Q is dense.
Q is dense.
But this thing it should be nowhere. Q
Why?
is dense only.
No. Q is so Q closer is whole of X, so it will be empty set. It will be empty set. So A is nowhere dense, but A Q is not nowhere dense set.
What I'm saying, X minus A closer. Say what we wrote. That is some set. That set we can take it as Q.
That you want to take as a Q.
Then that complement is nothing but that Q irrational. Because
In which space you are talking about?
I'm talking about topology space. Usual matrix.
Usual metric space. Let's say you have X minus A closer equals to Q. Now, is it possible? Is it possible in usual topology? A closer is a closed set. X minus A closer is an open set. Is Q open? That is not possible. No. That is good night. Zoom.
That is the case.
Too big. Why zoom out? There as well?
Percentage.
100%.
No, less.
Okay, little bit fine. Okay, so not nowhere dense, not nowhere dense does not imply it is dense. Fine. I hope that more or less you have idea of what we mean by nowhere dense. Okay. Let me move a little bit. Definition. A subset A is called meager. So a subset. So whatever we are discussing under a topological space. Okay. So a subset A of X is said to be meager or of, okay, so another name, that's a new name people use. In old days, people used to say mega set. Very good. Okay. What's going on? Or of or a set of first category. Sometimes some people say first their category. Okay, so we are saying said to be a mega set or a set of first category. Okay, if A can be written as countable union of set AN, where each AN is a nowhere then set. Each AN is a nowhere. Why do ink become other? Oh, this one. Nowhere dense. Okay, it's. So we are saying a subset is of first category or meager if A can be written as union of countable union of nowhere then set. Okay. So countable union of nowhere then set will be called a meager set. Okay. So if a set is a not meager, then we will call a set of second category. Okay. So a non-meager set is known as a set of second category. So if a set is not meager, that means non-meager set, okay, then it will be called a set of second category. Now we have a complement. Suppose the set is a meager. Consider a complement of a meager set. It will be called omega. Okay, complement meager. So that's why it's called omega, also known as residual. Okay, so a subset A of A is called a co-meager, also known as residual, if X minus A is meager. This is called co-meager or residual if it's complement. So complement of a meager set is called co-meager. Just remember this complement. From there we have the co words co-meager, complement meager, and also known as residual. Okay, residual subset or co-meager subset. Let's see example. Let's consider R with usual topology. Let X equals to R with usual topology. What about Q? Can we write Q as a countable union of nowhere then set? Obviously, we can write. Because we will take a singleton. Singleton are nowhere then set. So it will, and Q is a countable set. Okay. You can write R belongs to Q itself and singleton. So this implies that is a set of first category. In fact, any countable set is of first category or a major in R with usual topology. Okay. So in fact, any subset, any countable subset of R, it's time for break. Please remind me when. Okay. But we'll continue the next session. Okay. In fact, any countable subset of R is a mega. Is mega in R. So Q is not a no-hard set, but it's a set of first category. In fact, any countable set is a set. Okay, what about that means because Q is mega, so set of rational number is omega. Okay, is it a second category? That means it's not. Okay, be very careful. It might possible the residual set, omega set itself can be a mega set. Consider X as a finite set. So in that case, it might possible that its complement is also a set. If we consider Q as a subspace of R, for this same example, if we consider Q as a subspace of R, now whatever subset of Q will consider, that will be mega, and its complement is also going to be. Is it? Okay, we have to check it a little bit. But first, in fact, any countable subset of R is will just take as an exercise whether it is true or not. Q with subset topology of R. Okay, I mean with the usual topology, so you get the subset topology on Q. Now consider a countable or any subset of Q. Will it be a maker? Okay. That's the thing. Will it be a maker or not? Has to be, right? Okay, let's say. So Q, consider Q with usual subspace topology. Okay. A is a subset of Q. Okay. A is any subset of Q. Now, what is the closure of A in Q? We have a theorem. If you consider, because A is also a subset of R, so closure of A in R, okay, and then you take the intersection with Q, you get the, yeah, that set itself, okay. So you have to specify what type of set you are saying. Okay, let's say set of all integers. Let's take set of all for simplicity. J belongs to K. So J closure in R is J itself. Okay. So now J closure in Q is J closure in R intersection with Q. So J intersection Q will be J itself. Okay. So therefore closure of J is J itself. Now whether it has any interior point or not, that's the question. So now if you consider a point A belongs to J, so what will happen? So okay, again you can use the same formula. Interior of J in R, if you take the intersection with Q, you will get the interior in R. So the whole space and then take the intersection, you will get that. Otherwise, you can also check. Let's take a point, take an open neighborhood. it will contain rational number as well as irrational numbers. But if you take the intersection with Q, it will contain rational numbers. So obviously that means what? It cannot be inside of Z. So interior of Z bar is pi in Q itself. If you consider that interior of closure of Z, that is the Z itself, and which is pi. So Z itself is a nowhere then set. Okay. So obviously that means any finite set will be nowhere then set in this case. So again you have the same. So or any countable set will be nowhere things in this case. What will happen? So in Q, if you have choose a set A, it will be nowhere things, and its complement is also countable because Q itself is countable. So it's if you take a subset A of Q, it will be meager because it's countable. Because you can write union of the elements of the set itself, and you have only countable many elements. So it's meager, and its complement is also countable. So it's also going to be a meager. So that means what ultimately what I want to say that if we have a omega set, it does not mean that it is a set of second category. It might possible that a omega set itself is a mega set. So that means it's a set of first category. But now the question is whether set of all rational numbers is a set of first category or second category. It's a omega set. Set of all irrational number is a omega set. So we learned that till now in usual topology. So R with usual topology. Okay. So we are considering Q over here, and we learned that this is a mega. So now R minus Q obviously going to be omega. Now my question is whether R minus Q is a mega or non-mega. What do you think? It's not countable, does not mean that, but you have to be little more. Okay, now the question is whether union of two non-mega set, a mega set is a mega or not. Union of two mega set will be mega itself. Okay.
So R minus Q cannot be mega.
Then we need something else. Okay. So omega till now we can say, but whether it's a mega or not, we need a little more theory to prove it whether it's a non-mega or not. Okay. But at least you can say that, okay, at least we can answer the question whether union of two mega set is a mega or not. It will be, because we have countable union of two countable collection, it will be countable. Okay. So actually, in fact, it will be non-omega, right? Non-mega. We will see that we need a theorem which will say that okay, this it satisfies this property, then it will be like this. Because R will be a set of second category. So because of that, R minus Q will be not non-mega. I mean not non-mega set basically. It's a set of second category. We'll prove it after some time. We can discuss. At least we can say it's a omega. Any other examples? Actually, if you consider any perfect space, okay, so let X be a perfect topological space. Then any countable set in X. Okay, I should define first. Okay, let me. Then any countable set, any countable subset of X is of first category. Any countable set will be a set of first category. What do you mean by perfect topological space? A topological space is said to be perfect topological space if it has no isolated point. So all points are limit points. So other way to say, a space, topological space is said to be perfect if it has no isolated point. Now, how to prove that it is a set of first category? Any countable set is a set of first category. Is the set, let's consider J as a subspace of R. Is it a perfect space? No, it's not a perfect space. Okay. Anyway, so any countable subset of X is the first category. How? So you see, if we have a countable set, let A subset of X and A is countable. Then what we write? A equals to union small a belongs to A. Now singleton A is a no-hat set. Why? Because this cannot be an open set. Why again it cannot be open set? Because if singleton A is an open set, then that means singleton A is an isolated point. Correct? Isolated point means what? So there will be an open set containing the set A itself. So this implies that singleton A is a no-hat set and hence A is a set of first category. Okay. Singleton A in a perfect space is no-hat dense. But it is not true in a discrete space type of thing. It cannot be an open set. That's the thing. And obviously that means it cannot have an interior point. Right. Obviously we know that singleton A is a closed set. All we are discussing in a T1 space only. Okay. So before I move into other example, let me put it in this way, whether it is true or not. Because in tutorial we are not going to have a tutorial session. In the meantime, I'll ask you a question and like solving ideas and tutorial. So let's say we have this example. X is a second countable space. Let X be a second countable space and let even be a countable basis. Okay, second countable space means it has a countable basis. Okay. So consider the following set. Let's say A equals to union A equals 1 to infinity, even closer minus even. Is it negative? Even closer minus even is negative. So if you can prove that even closer minus even is nowhere then set, then you can say that it is negative. So is even minus even is a nowhere then set? Okay, let me move ahead because it will take time. Okay, so try to prove that this will be a mega set. Later, think about it. Okay, let me define a few more things. So, what happened in topology, or even in other places, we always think about whether there are set, like when we discuss about countable, uncountable, all this type of things. Especially in set theory perspective, whether the set is a big enough or small. So, smallness is defined. Like in general, we say the countable set are not that big, small set. Uncountable set are big. Or if we have a set of measure 0, then it's a small set type of thing. So similarly over here, we just want to say that whether it's a big enough or small enough. So actually, we mean by mega sets is like a small type of set. Residual set, on the other hand, can be small, can be big, but we have to check whether it is a second category or not. In general, we assume that residual sets are big set. Unless the space itself is countable, we'll say that residual sets are a big set. Or if we have a set of second category, it's a big set. In that sense. So in general, in a set theory, we define a set as big or small based on the following criteria. What is the criteria? We'll say that to define that, let me put in this following way. So let X be a non-empty set. Non-empty set. Let I be a collection, a non-empty collection. Okay, a collection of subsets of X. Then I is said to be an ideal of X, ideal on X. Then I is said to be an ideal on X. If first thing is that empty set in I. Second criteria, if A be in I, then A union B in I. And third criteria is that if A is subset of B and B belongs to I, then A belongs to I. So, if we have a collection of sets which satisfy this property, then it will we call it's an ideal. Similarly, so in the second criteria, second property, we replace by finite union by countable union, then we have the notion of sigma ideal. Okay. So if we replace 2 by, let's say, 2 double dash, what it is, if you have an belongs to I for n belongs to n, then union an belongs to I. Then I will be called a sigma ideal on X. So I will be called a sigma ideal. It will replace finite union by countable union. What happened?
The third condition doesn't imply first one. Like empty set is contained in P.
Yeah, so you don't know whether I have empty collection. If there is no collection, then what will happen?
So that is a non.
No, that's why I forgot to put. That's why later put empty set belongs. Otherwise, you don't need.
Suppose I is non-empty collection.
Then we don't need this. Okay. Now, this if we have a collection of subset, like Okay, look over here. You see that mega sets. If you take the mega sets, we know that union of two mega sets is a mega set. Correct. And if a set is a mega, then its subset is also a mega. Why? We just take the intersection of that and we have it. So if you collect I with a collection of all the mega subsets of a space, it will form an ideal. Okay. So let I be the collection of all mega subsets of X, then I is an ideal. Similarly, you see that if we consider, okay, will it be a sigma ideal? If you union of countable union of mega set will form mega set. Yeah, it depends on the cardinality. So in general we cannot say. Or we can say countable union of countable set is countable. Can say. So it will also form a, so let's say, or we have n, we have union of countable union of no set. So now we have a countable union of countable set, so it will obviously going to be neighbor. So it does not depend on the cardinality. Here. Okay. So that means that will also going to form a sigma ideal. So not only that, in fact, a sigma ideal. So even you see that, so what we are saying, we are now will say in general, for topological space is fine, but in general in set theory, we'll say that a set is small if it belongs to some, some sigma ideal. With respect to some sigma ideal, we'll say that okay, this set is small. So you define like here your sigma ideal is a collection of all mega sets. So in that sense, in the space, if we form a sigma ideal, okay, then you will say that a member of sigma ideal is small. If it is not a member of sigma ideal, it is big enough. Okay, so that's how we define in general in the set theory whether a set is small or big. Depend on whether it's in that sigma ideal collection or in the sigma ideal collection or not. Obviously, it depends on one set. Obviously, you can form a sigma ideal. But suppose you first define a sigma ideal. Now, with respect to that, whether the set is big enough or not, you can define it. So that's the idea. Okay. What is the set of no-Huygens set? So whether union of two no-Huygens set is no-Huygens. Let's say A, B, both are no-Huygens set. Oh, I think Z can. Okay, just let then we'll have it. Let A and B be two no-Huygens sets. Will A union B is no-Huygens? Will that be a no-Huygens set? Should be. Why? Closer. So okay. Okay, think about the other way, denseness. So we know that X minus A closer will be dense. x minus b closure will be dense. Okay. That means whatever open set you will consider, it will intersect x minus a closure, x minus b closure. Okay. So can we say that it will also going to okay, think this in the place. Where x minus a closure is dense, x minus b closure is dense. Can we say x minus a union b whole closure is also dense? Okay. Okay, we'll meet again after 15 minutes.
I cannot see the. You make it so big. I want. Don't want that.
You can't see what?
The time and all that.
Oh, okay.
There is an open set V of U, now it is such that V intersection A equals to 5. Suppose you know this condition. That's your task to prove that you are always going to find an V such that V intersection A equals to 5. A is known as dense if and only which for each open set U there exists an open set V which will be subset of U such that V intersection A is equal to 5. So if we have this condition, from there can you find the solution? That means can you find an open set U, whatever open set will be given, can you find an open set V, intersection of A union B will be. Now I think it is very easy. Let's try. Okay, let's say you have an open set. I have to go a little fast. So let's say you have a given open set. Let U be given. So since A is nowhere dense, since A is nowhere dense, what will it imply? That there will exist an open set B subset of U. Let's say B subset of U such that V1 intersection A will be empty. Since B is nowhere dense, okay, I'm just writing this. Then what will happen? There is V2 subset of U such that V2 intersection B will be empty. So what should I take as a name? V1 intersection V2 will be the open set. So then V1 intersection V2 intersection A union B will be empty, and this proves that whatever open set you have, you can always find an open set such that A union B is equals to 5. So therefore A union B is a no-hat set. If we know that this is then A union B is nowhere. So actually, go to template. So this is another condition you can prove. A is nowhere dense if and only if for each open set U there exists an open set V subset of U such that V intersection A equals to 5. Okay, that's you have to prove. Okay, one part I am telling you how to get a P. Other part you just prove. So one part you see whatever open set you will have. Because x minus a bar is dense, what will happen? U intersection x minus a bar will be non-empty. Okay, by the way, this is a non-empty open set, I mean to say. Otherwise, it has no meaning. Non-empty open set. Otherwise, it's obviously going to be empty. So, U intersection x minus a bar equals to 5. And then you take V equals to U intersection x minus a. Then you can see that intersection with A is empty. Okay, just a minute. I think this is problem I'm facing over here. This V1 intersection V2 can be empty. So then what will you do? It might be easy. So then you cannot go by this. But there is a way to remove this problem. Okay, you got it. My problem, because V1 is fine, V2 is fine, but if you take the intersection, it might possible that this becoming. Then it will not. So what you can do for V1 is fine. Now for this V1, there will exist a V2. That will be empty. Now this V2 will be present. A and B. That's the thing. Now for you get V1. That's fine. Now for this V1, you're obviously going to get a V2, for which this V2 intersection B will be empty. Get this V2 and you have the answer. Yeah, V2 contained in V1. Well, because what is the criteria? It says that for each open set U, here will exist a non-empty open set B subset of U, such that B intersection A will be empty. Now think about in place of U we have V1. For V1 you will have a V2, such that V2 intersection B will be non-empty because B is no matrix. Okay, so this proves that union of two no-hat dense set is no-hat dense. Is countable union of no-hat dense set is no-hat dense? Is countable union of no-hat dense set is no-hat dense? It's not. Can you give an example? Q. Because in single Q, all singleton is no-hat dense set. But if you take the union of this, we already proved that Q is not no-hat dense set. Therefore, countable union of no-hat dense set might not be no-hat dense. So, a countable union of no-hat dense set might not be no-hat dense. Okay. Example, for example, Q can be written as a countable union of no-hat dense set in real life. And Q itself is not no-hat dense. One more problem exercise, then I'll prove the theorem. Example or exercise, because we are doing it simultaneously. Can you prove that a set is co-major if and only it contains intersection of countable family of dense open sets? Prove that a set is co-major if and only it contains a countable family or contains the intersection of countable family of dense open sets. Can you prove this? Prove that the set is co-major if and only it contains the intersection of countable family of dense open sets. Co-major means what? Its complement is major. Now we have proved that. You just think that way, no, nothing will come. You have to write on the paper. Okay, one more minute again. At least one part.
X minus unit of those Bn is zero. That will be the intersection of X minus B.
Which part you have to?
Minus A is omega means.
Okay, so let's go one by one. Let's say let A be meter. Sorry, co-meter. Correct. Then what will happen? X minus A is meter. Okay.
The next minus A.
So X minus A will be union of Bn, where each Bn is nowhere there. How to So that means this will be inside intersection of this will be.
In other words, A is equal to X minus.
Yes, that's what I'm saying. So that means A is X minus intersection of. Okay, so want to write whatever. So first write that. From here you can actually go. So this you can write as what you want to write A equals to X minus union N equals to 1 to infinity Bn, and this is same as intersection N equals to 1 to infinity X minus Bn, and then you is it then solve. Now you are almost done. This is this contains what? X minus Bn. Actually, we don't need that. We need X minus Bn. Now these are open n sets. Yeah, so Bn is in Bn closure. So X minus Bn containing X minus Bn closure. That's how this intersection is formed. If you take intersection of this, countable. So obviously this will be bigger than this. This is fine. So therefore A contains countable intersection of planes open set. Okay, you just reverse the process, you will get the other way. So don't want to spend time. So it's fine. These are all planes open set. Planes. Other part will just write that way and just have to do it. Okay. The next theorem Let X be a topological space, then the following statement are equivalent. Let X be a topological space, then the following conditions are equivalent. What are those conditions? First condition, every open set is a non-mega set. Every open set is non-mega in X. Second condition, every omega set is dense in X. Every omega set is dense in X. Third condition, any countable intersection of dense open sets of X is dense in X. So these three conditions are equivalent. So if an open set is non-mega, then it will imply that every omega set is dense in X. And third one, it will imply that any countable intersection of dense open sets of X is dense in X. Let's try to prove this. One implies two. So we assume that every open set is non-mega. What you have to prove? You have to prove that every omega set is dense in X. Let's say we have A is a omega set and it's not dense. A be a omega set in X. Let's go that way. Let's A be a omega set in X. That means what? X minus A is mega. X minus A is mega in X. That means what? X minus A closer is X minus A closer is dense in X. That is X minus A closer, whole closer is equals to X. And this is nothing but what? A closer equals to X. Therefore, A is dense in X. So this proves that every omega set is dense in. Okay, 2 implies 3. Any countable intersection of the open set of X is dense in X. What you have to assume? Every omega set is dense in X. Okay, so 2 implies 3. So we assume every omega set is dense in X. Okay, let's say let UN be a countable collection of dense open subsets of X. We have to show what we have to show? Intersection UN is dense in X. It is very simple. Why? Exercise. You put this theorem, what exercise you need? If it contains a countable intersection of dense set, then it is co-maker. That means this set itself is co-maker. So therefore we can say that it will be dense. Or other way you can say that. So is omega by the last exercise. Hence by 2 is dense. Now 3 implies 1. What you have to show? You have to show that every open set is non-maker, assuming this. So let U be an open subset of X. Let U be an open subset of X, we have to show that U is non-maker. We have to show that U is non-maker. What we will do, basically, we will assume it's a maker. Fine. Suppose U is maker. U is maker. Then what you can say? It can be written as a no has been set 1. Another thing you can say that from there we have to get a contradiction. So X minus U will be co-maker. So it will contain an intersection of dense open sets. Yes, that I think. Suppose U is a maker, then X minus U contains a countable intersection of B, a non-empty, basically B a non-empty open set. B here is right a non-empty open set. Otherwise, obviously it will be maker. Empty set is your maker set. So X minus U contains a countable intersection of dense open sets, and by 3, that means what? Countable intersection dense open set is dense. So that means X minus U itself is dense. Okay. So by 3, X minus U is dense. in X. Thus, X minus U closure is X. And this proves that U is an empty set. Why is U is an empty? But it is not possible. Well, which is a contradiction. Why? Which is not possible. Which is not possible. Because X minus U intersection U is empty. U is an open set, but it's not intersecting X minus U. So therefore, X minus U cannot be X. It cannot be tens. That's the thing. So hence, which is a contradiction. So hence, U should be non-negative. Hence, U is non-negative. This is C. Countable intersection of dense open set is dense. So a set is containing a dense set means the set itself is dense. It's a figure. Because it's a complement.
X minus U is closed. So its closure is equal to itself.
Yeah, that's also you can say that's closer will be equals to itself. So that's also not possible. That implies that U should be empty. That's also possible. Because X minus U is open, closed. Its closure is X minus U equals to X. This implies that U is empty, but U is not empty. That's also another way of writing, making a contradiction. Whatever. Okay. So there is by the way. So what are the conditions we learn? Every open set is non-negative in X. Every comega set is dense in X. Any countable intersection of open sets of X is dense in X. So these are the three properties of a space are equivalent. Now, based on these properties, we are defining a space. We'll say that a topological space is a bare space if it satisfies this equivalent condition. Okay. So here is our main definition. Actually, that is here on is basically. So a topological space X is said to be a bare space. So B-A-I-R-E, bare space. If X satisfies equivalent conditions in the above theorem. That means what? That means we say that a space is a bare space is if every open set is non-negative, or a space is a bare space if every comega set is dense, or you can say that a space is a bare space if every countable intersection of dense open set is dense itself. By the way, there is a name for countable intersection of open sets. So a countable intersection of open set is not countable in general, right? Not open in general, but we call this type of set is a G delta set. So you will find that definition as well in the internet or in a book. Space is called bare space if every G delta set dense, is basically dense. You have to little bit change it here and there. It's like that. Okay. These are the things. Now we prove. First, one by one we'll prove. First, we'll prove that every open subset of X is a bare space. So if we consider U as a subspace, will be a bare space. So let me put that here. Let U be an open subspace of X, and X is a bare space. Then U is a bare space. So every open subspace of a bare space is bare space itself. Let's try to prove this. Do you have any idea how to prove it? Then, which definition you want to use? Okay, so that means countable for intersection of open then set is dense. So now you need a countable intersection of open set. Okay, so as we say, let's take let UN be a countable collection of open dense sets in U. So that means each UN is open in U, not in, I mean, it will be, but we are assuming that UN be a countable intersection of open dense set. So they are all dense in U and they are all open in U, not in, we are not talking about X. Okay, what we have to show? We have to show intersection UN is dense in U. Okay, now, so UN is countable as a dense open set. Now, can we say that they are also dense open set in X? Yes, it will be, because we know that if a subspace is open itself, then any open set in that space will be open in the whole space. So since U is open, each UN is dense, it is open. Since U is open, U is open, what you can say? Yeah, UN is open in X. Then what we do? Take UN union X minus U whole closure or something like that. Then you will get a dense in whole of X. You know that even closure is equals to U. That you know. In U, but not in X. Yeah, so we have to make something little bigger, that picture. So it's an open in X. Okay, what about this? Then even union X minus U closure, X minus U closure is open in X because it's closed, and then we have this. Now what? So are they dense? Even closer is U, and this will give whole picture. Correct. So this is dense in X. Is it clear? Is it dense in X? Whatever open set you consider, okay, either it will intersect U or X minus U. Any open set, either it will intersect U or X minus U. If it intersects U, then intersection with that will intersect UN, because each UN is dense. Or otherwise it will intersect X minus X closer. Okay. Or whatever, if you take a closer of it. Equals to what? A union B closer is A closer union B closer. So even closer union X minus E closer. So even closer is U union X minus E closer. Oh, it's not over, sorry. Not full. Even closer is okay. We are taking closer in. Then closer. It will contain U at least. It will contain U. Even closer obviously definitely contain U. It is containing U, and so it will be dense. It will contain U. So this is containing U. That's fine. One thing. And second thing is that it also contain X minus E closer whole closer. So X minus E closer is so A intersection B closer. Okay, let's say it is dense up. Then we'll see what we can do. If we suppose we can prove that it is dense, UN intersection union X minus U closer is dense in X. So since X is a bare space, we take the intersection. So since X is a bare space, so intersection of this union X minus E closer is dense in X. So what we have, even intersection X minus U whole closer, X minus closer is dense in X. I mean intersection of all these. So this is same as, so you see this is dense in X. So can we say that intersection of U will be dense in U? Is dense in X. So can we say that intersection of UN is dense in U?
Union X minus U.
Oh, sorry. Got it. So, like, if you consider an open set in U, obviously that is not intersecting that part because it is other side, correct? So let's take an open set. Let W be an open set in U. Then W obviously not intersecting X minus U closure. So this is fine. So that means now W is open in U, W is also open in X. So W is open in X. So therefore it must intersect this. So hence W intersection UN should be non-empty. So this proves that intersection UN is dense in A. This is fine. W be an open set in U. So that means then obviously W cannot intersect X minus U closure because W is a subset of U and U is contained in U closure. So obviously cannot be in X minus U closure. So W intersection this is an empty set, but W is open in U and U is open in X, so W is open in X. So that means W must intersect because it is dense, so W must intersect there. So hence W intersection, this part should be non-empty. So that means this is a dense word because W is in any open set in U and it is intersection with this is non-empty. So this proves that this intersection is dense in U. Right. So in this proof, only thing missing, you have to show that this is dense in X. You have to show that that is dense in X. So now let's see whether you can show it. Let's spend 2 more minutes. Okay. So dense in X means whatever open set we have, it must intersect that. So let's take an open set. Let X be open in X. So can we say that this is intersecting that? Let X be open in X, and we can say that S intersection U is open in U. Therefore, S intersection U, intersection of UN not equals to phi. So this, yeah,
This intersection is not.
non-empty. So that means S is intersecting UN. Yeah, if it is in U. Okay. Yes. If it is non-empty, then it is intersecting. Yeah. But let's say it is empty. So if S is empty, equals to 5. But U closure, yeah, because U closure it must, will it intersect? Yeah, it is contained in X minus A, X minus U closure. If it will mean that case is containing x minus u. In that case, can we say that it will intersect x minus u closure? U is a subset of u closure. X minus u subset of x minus u closure. It's contained, so it's not contained. Check whether if it is dense, then that too will work. Okay, this too will work. You have to think little bit whether it is working or not. Another way, let's say we can prove that whether it's an open set is non-mega or not. That's the thing. So like, let's say that we have an open set W is open in U. So now W is obviously open in X. X. So it is non-co-maker over here. So W is non-co-maker. Okay, suppose W is maker in U. That means what? You will have a no-hat dense set. Not sure whether it will work. You will have a no-hat dense set in U. But it might possible that from the whole space. Okay. Suppose we have an interior of some W in subset of U. So this interior so the problem is that suppose you assume that W is open in U and W therefore this will imply W is open in X because U is open. Now let's say that W is a sum of maker in U. That means W can be written as countable union AN where each AN is nowhere dense in U. Can we say that AN is also going to be nowhere dense in X? Can we say each AN will be nowhere dense in X? U is given as open set. If it is okay, then we can go ahead with this. So AN is nowhere dense means what? in U means x minus an closure is dense in U. Okay. So can we say that that will be dense in X as well?
The set is longer than second that you set that exists.
Yes, we can also use that An is known as dense in U. Means for whatever open set we will consider, there will exist an open set with intersection. So let's say W, okay. Let's say H be open in X. Okay. H be open in X. We have to show that there exists a non-empty open set which intersection with we have to find a non-empty open set E of S such that E intersection, what it is, let's say n equals to 5. Now again the same problem, S is open in X does not mean that it will be intersection with U is the problem.
If it intersects with you, then we can use.
Yeah, with
Otherwise,
U.
we can, if it doesn't intersect with you, we can take S as E as S only. We will get that S intersection.
Oh, because A are the elements of yes, correct. Yes. Then it is working. So let's say what C say that let's say S which will intersect with U. Okay? It's a non-empty. Then this will be open in U. So there will exist an open set of U. So there will exist an open set E U of U such that EU intersection AN will be 5. But since EU is open, EU is open in X. Since U is open, EU is open in X. So therefore we got that. Another possibility is that S intersection U is 5. And because AN containing U, so S intersection AN will obviously going to be 5. So this proves that each AN is also nowhere dense in X. So therefore we got the solution. So now what is the reason? So W be an open set in U. We want to show that W is non-major in U. Now suppose W is major in U. By suppose on contrary, W is major in U, then W can be written as countable union of nowhere dense sets. Now these prove that each AN is nowhere dense in U. But we proved that AN is nowhere dense in X as well. Now X is a bare space and you are writing an open set W as a union of nowhere dense set, which is a contradiction. So therefore, even W cannot be a non-major. It cannot be major in Q. So this is the proof basically. But that proof I think that denseness, yeah, that also I think can be proven. Little more effort is needed.
X minus U is close to us. Can we say use that?
X minus U is
Closed. Since U
closed. Okay, that is closed. So
X minus U is can we use that?
X minus U closer will be X minus U itself. Okay. We'll get that. X minus U, yeah, I think it will work. X minus U subset of contains X minus U closer, correct? So x minus u closure will contain x minus u closure. So that means x minus u. Oh no, actually repeating it is the same thing. Yeah, it will it is. I think it can be proven, but little more calculation is needed. Please do the calculation later and let me inform if you got the solution. Okay. I mean, please inform me if you got the solution. And if I got it, I will take it. So this is another way to solve the problem. Anyway, so what we learned that an open subspace of a bare space is open. So next, I'll just ask you to prove this theorem. Actually, I already proved this theorem, and this is a main theorem we'll prove. That is known as bare categoric theorem. Okay, that is a very important theorem in metric spaces and topological spaces, especially in metric spaces. Okay, no, this is the theorem. This says that let X be a complete metrizable space. So you can think about X is a metric space, complete metric space. Or similarly, you have locally compact space. If we are considering a topology instead of a metric space, then X is a bare space. Okay, in locally compact, house roughness is already I assume, so X is at least satisfying house roughness. So then X is a bare space. So let X be a complete metrizable space, or similarly locally compact space, then X is a bare space. We'll prove. This is known as bare category theorem. So any complete metric space is a bare space. But the converse is not true. There are some examples, like one is Gaussian space, which is a bare space but not a complete metric space. And even you don't need to be that great example. Consider a topological space which is locally compact. So that's obviously not a metric space. Then you can find in internet there are database, the database of spaces. So define database of topological spaces, which will give you what type of property that topological space have basically. Okay, let's prove. So let's say we have a sequence of open the countable sequence of things. Let UN be a sequence of open dense subsets of X. So we consider a sequence of open dense subset of X. What we have to prove? We have to prove that intersection UN is dense in X. Okay. We prove that their intersection is dense in X. How to prove a dense in X? If we can show that whatever non-empty open set we have, if we intersect with this, then we are done. So it is sufficient to show. So let U be and sorry, not let U be a non-empty open subset of X. U be a non-empty open subset of X. It is, or we have to show this. We have to show that U intersection UN is non-empty. Then we can say that intersection of UN is dense in X. Good. Since U1 is dense, okay, so U1 intersection U is non-empty. Since U1 is dense, U1 intersection U is non-empty. Let's take a point, x1 belongs to that. Let x1 belongs to U1 intersection U. So then there exists a ball, because it's a metric space, there is a ball of radius 1 or half, whatever you want to take, center x1 contained inside of that. So then there exists a ball V1 centered at x1 of radius half, such that V1 x1 comma half, or not V1 x1 comma half, or radius less than half, basically, I mean to say. Okay, you take radius less than half, such that V1 closure is contained inside of so many. Okay. V1 contained inside of U1 intersection U. Okay. So we have a ball of radius less than half. So we don't know exactly what is the radius of the ball, but its radius is less than half. Otherwise, you can have a ball, and its closure is contained inside of that. Whatever ball you have, you can always get a smaller ball whose closure will be inside of it. It's always possible, because it's a metric space. This is whatever R1 take R2, still less than. If you take the closure of that, will be inside of it. It's also true in general regular space. So anyway, so we have like this U1. Okay, next is that since U2 is dense, so V1 intersection U2 is non-empty. Let X2 belongs to V1 intersection U. Then let's say V2 be a ball centered at X2. So let V2 be a ball centered at X2 of radius less than 1 by t square, such that V2 closure is contained inside of V1 intersection U. So we'll proceed in this way. Next, V2 will intersect U3. Okay, and we'll go one by one in this way. it will go in this way. So we generate a sequence of sequence of numbers, which is inside. You see that it's inside a ball. This will become a Cauchy sequence. So this will generate. It will continue this process if we continue this process. We will get a Cauchy sequence etc. Okay. We'll get a Cauchy sequence etc. Because the ball is becoming lower and lower and lower. Okay. Thus that because it's a complete metric space, it will converge and it will converge to such that xn will converge to a number inside of all this BN closure. Like whatever we have choose, B1 contain B2, B3 contain B4, it's like that. So it will be in all this thing. So x belongs to x to this, and this is same as this if you take the intersection, and this will be subset of U intersection UN. So this proves that U intersection UN is non-empty. So this proves U intersection union, not U intersection, sorry. Yeah, actually it's very difficult to teach for 3 hours. Anyway, okay. So this proves that intersection A UN is non-empty. So hence intersection of UN is lanes in X. Closure is intersection is same because what is happening B1 is containing B2 closure. So you have like that. B1 containing B2, B1 closure containing B1, and then it is containing B2, it's containing B2, and then we have containing B3, and like this. So because of that, intersection of their closure is that intersection of Bn. And it is a Cauchy sequence. Why it is a Cauchy sequence? Let's take any two numbers. Then each one greater than j. So then there will exist a belongs to natural number such that let's say 1 by e to the power k is less than xi. A little bit adjustment is there. We will do it. So if you now take m greater than equals to k, if you take m greater than equals to k and consider xm and xn. So what will happen? Both xn and xn will be in Bn for n greater than n. Correct? The way we have constructed, it will be in Bn. So now what will be the distance between them? Will be obviously less than equals to the diameter. So distance between these obviously less than equals to the diameter of Bn. Because both elements are over there, we choose n greater than equals to k, and let's say n is greater than n. So obviously one of them will be bigger than the other. So therefore xn and xn both in Bn. So now if we have two elements in a set, in a ball. So distance between that two points obviously will be less than equals to the diameter of the ball. Now the way we have constructed, diameter of the end cannot be more than 1 by 2 to the power n minus 1 because the 2 to the power n basically. For B1 we take radius 1 by 2 to the power 1. No? Yeah. So radius for 1. So it cannot be over 2 to the power n minus 1. Okay. The way we have constructed, so this is obviously going to be 2 to the power k and then we have this inside. This proves that xn is a Cauchy sequence. Is it clear? This proves that xn is a Cauchy sequence the way we have chosen. You can make a minus 1. Just make it an adjustment. Do the adjustment over here. So that proves that this is a Cauchy sequence, right? Yeah, now it's a Cauchy sequence. So that means it will converge to some number. Okay. So where it will converge? We are saying that it will converge to its intersection. So whatever intersection you have over here, it will converge to that point. That's your task to prove that will be over here. Okay, so definitely it will converge to some number. Now prove that it is in their intersection. Let's close the intersection. So that's a part for the completeness. If you have a completeness, then you can prove this one. More or less proof is clear what we did. So we have open set, use the property of the open set and take a ball of small radius so that we can form a Cauchy sequence and then we can use that the metric space is complete. So Cauchy sequence converges to a number. So that number will be in their intersection. The way we have constructed, it will be intersection of the enclosures. We have to keep mind that it's a reducing size over there. Now, if you have a local compact space, the thing with that, this actually will be non-empty. The way we have defined, so this sequence ness will not be here. So try to prove that using the finite, what is called? I forgot the property. Finite intersection property of compactness. Using that, try to prove that this will be non-empty. This part will be non-empty and it will be done in that. I mean, prove that this part is non-empty. You will not going to have a ball type of thing, but you can make such a. Okay, that's all for. Yeah, Cantor intersection theorem you can also use for this case because it's a mesh case. Yes, correct. Okay, any question?
That is how we will.
This is complete metric space.
It is complete.
That is a possible.
Converge to x. Then xn will converge to x. But how do we make sure that x is in the intersection of
That's I asked you to prove. That's your exercise to prove. That x will go over here. As Cantor intersection theorem says that definitely there will be a, as he said, if we have to use a Cantor intersection theorem, what is it Cantor intersection theorem? If we have a mesh state, closed sets, then if you take the intersection of it, it will be non-empty. And contain only one point. That's the other important thing. It will contain, and this is nothing but that point. Its completeness is needed. A complete metric space you have vector intersection. We have most of us to think real analysis. That is a complete metric space. There we actually use the property of completeness. But it is also true in general metric space, complete metric. Okay. Next up, I will just touch again because I don't think proper and also like difficult for me to teach for that long time. Okay, I will just take one session. Second up, you will choose if you want to. I will just touch little bit of game. If you want, otherwise I will continue this one. What do you prefer? Shall I continue VR space or just little bit of game and just discuss? Okay, I will discuss little bit of game. Actually, all this needs many lectures. Very difficult to cover everything in one lecture, and it's something new. You have to go very slowly. To go, I am unable to. I mean, sometimes I am trying to resist myself to go further, but again I was thinking that at least I have to cover it. Okay, that means another thing is that now can you say that the set of all irrational number is non-major? R is a complete metric space. So complete metric space is a bare space. So now how are we going to relate this to?
Cannot be written as form over. Suppose it be possible that this irrational number is
Okay, first let's try to show. We know that union of two mega set will be mega. So if we can prove that a complete R is a non-mega, then we are done. Then set of irrational number will be non-mega. Now we prove that a complete metric space is a bare space. So from there, how can we say that a bare space is a non-mega space, is a space of second category? Every open set is non-mega and the space itself is open. So it is therefore non-mega.
Any question from the online participant? Okay, then we meet again around 2.